So our first fundamental relationship is going to be equilibrium. We'll put that up here in the corner. And what we're going to do, we're going to draw some pictures here, and we're going to talk about the pictures. So first off, we're going to start with the rod. And that rod is going to have a coordinate system. So we'll put x going in that direction. And it's also going to have some area, a of x. And we're going to assume that that area changes fairly gradually so that we don't have any abrupt changes that we need to worry about. And we're going to put some forces on this guy. So we have some force per unit length. It's going to go along the rod here. I'm going to draw that in orange. And I'm going to call that B of x. And that is some force per unit length. The other thing that we're going to have is we are going to have a stress. So I'm going to draw that here in blue. And you can think of that, that's a stress, so it's over an area. We're going to call that sigma of x. And that's going to be a force per unit area. And of course, we're going to have some stress that's occurring on the other side as well. And so now what we want to do is we want to take a little tiny slice of this rod. So I'm going to come in here and I'm going to select this little piece right here. And we're going to expand that out. So it's going to look something like this. Excuse my drawing skills here. So we have a B of x here at the top. We're going to have some stress here on the back end. And we're going to call that sigma of x. So the stress at x. On the other side, this front side, we're going to have a stress as well. And we're going to call that sigma of x plus some delta x. And what that means is I'm really indicating that the width of this slice that we've cut out is going to be delta x long. And all we need to do to come up with our equilibrium equations here is to figure out what's going on with our little slice here. So maybe I'll add a couple more arrows here so it's clear that this is a force per length. Goes all along the section. And so we know how to do equilibrium. We sum the forces, right? So we know that they should sum to 0 because we're in a static equilibrium. And what do we have? Well, we have on this side, we have sigma x plus delta x. And we should say that we still have some coordinate system here, and we still have some area. It's a function of x. To make our math a little bit easier, we're going to assume that area is the same on both sides. So I'm going to call that A. So now this is a force, right? Sigma x plus delta x times A. That's a stress times an area, so that'd be a force. Okay, and it's going in positive x. And we're going to add to that our picture here of B of x, which is a force per unit length. So what do we need? We need a length. That length is going to be delta x. And now if we look at our slice here, we see that on the other side, we have our arrows going in the other way. So that's going to be minus sigma of x times A. Okay, so we know that this relationship should be true. We can do a little bit of rearranging here. And if we do that, we can pull the area out front. So we say that 0 is equal to the area times sigma x plus delta x, minus sigma of x. And I'm going to divide everything through by a delta x. So now this is going to be plus b of x, delta x over delta x. So you can see now that these guys go away. And what we're left with is an equation that says 0 is equal to a times the stress at the right-hand side of our cut minus the stress at the left-hand side of our cut divided by delta x. And you probably are seeing where this is going already. What do you think we're going to end up doing? We're going to imagine that our little infinitesimal slice here gets smaller and smaller and smaller, and we're going to take the limit as that approaches 0. This is our common trick in calculus, right? And if we do that, if we say that what is the limit of this expression as delta x goes to 0, what we're going to find out is that we're going to get an expression that looks like this. So 0, we're still going to have the area. This now becomes the derivative of the stress with respect to x. We still just have b over there. Doesn't change that side of the equation. And here is our equilibrium equation. Put this in. So now we can see that if we know what our force per unit length is, we should be able to calculate our change in stress with respect to x. And we're going to use this later when we talk about building our governing equations. But it's good to understand that this is just an expression of equilibrium that allows you to determine what the change in the stress is for any given force per length.